The capstone speaker of this incredible symposium is Ralph Cicerone. Ralph Cicerone has been a major leader in science, in education, and in public service, and even in baseball. And he has made really significant contributions in all of these areas, and I think has had a tremendous impact on the world because of his leadership. And I think it's very special for us to have him as the final speaker. And he's currently the president of the National Academy of Sciences, and his topic today is putting science to work in developing science policy.
Thank you, John. I'm certainly enjoying today. I think one of the beauties of a career in science is that you make friends who become almost as important as some extended members of your family. And I've seen some of those old friends today, and making new ones, it really feels good. And certainly the subject of today has been enormously exciting and very important. This title of my talk isn't exactly what was printed, and it isn't the title that I chose. In fact, Mark and I can't figure out where the title came from. I thought he chose the title. He says my secretary did because I didn't furnish a title when I was supposed to. But when I saw the title, I said, why not? So give it a try. Let's see. So here's a quick outline of what I want to do. We've heard a tremendous portrayal of some of the facts and projections and deductions that people are making. I want to give just a quick version of my own background on the climate constraint that we're looking at, that we face, although this is obviously nowhere near the full story. And of course, the biggest part of that constraint is fossil fuel use to furnish energy. It's a huge challenge. And I want to go over some of the goals and constraints on energy pathways, but the issue there is that climate is not the only constraint. It's not the only challenge. And when you begin to mix in the other constraints and challenges we have due to energy needs and energy usage, the choices become more complicated. And the bottom line is something that won't surprise any of you, but I have just a few examples to illustrate why we really should expect more progress from science and technology than we're going to see from human behavior changes. And in fact, we're going to need it very much. So this is a cartoon of something that Jim Anderson referred to and other people did. Kim, it's from an old paper of ROM, 1989. Only I changed a couple of numbers here and there. To a first approximation, to a very good approximation, the Earth's climate is simply controlled by the planetary energy balance, certainly over periods of time that are more than a couple of years. And the input side of the energy budget is 342, slightly less than 342 watts per square meter, averaged over day and night and averaged over the entire year. About 105 watts, and I'm sorry for those of you who are looking at the other screen, but about 105 watts is reflected directly from the tops of white clouds and white shirts and reflecting water and everything else, snow and ice. The remaining 237 is absorbed by something in the atmosphere or Earth's surface. These numbers are all measured pretty well, so this is not just a theoretical calculation of a Stefan Boltzmann law or something from the temperature of the sun. That's not it. They're mostly measured pretty well. And as Jim Anderson pointed out earlier today, to be in a approximate energy balance, that means that 237 watts per square meter are radiated back out to space by the Earth atmosphere system, but the radiation from the surface of the Earth is considerably larger in black-body radiation. Now, the presence of a few greenhouse gases in the atmosphere, water vapor, carbon dioxide, and ozone, is just to emphasize several of the natural greenhouse gases. But if those gases didn't exist, we could calculate the temperature of the surface of the Earth very easily. In fact, we can do that calculation for Mars from measured sunlight, intensities, as well as the reflectivity of the surface of Mars, and we got the right answer. There are day-night variations on Mars, but you got the average perfectly. If you try to do the same calculation for Earth, you calculate a temperature which is sub-freezing. In other words, you underestimate the temperature greatly, and it's because of the greenhouse gases, as Jim said, causing more infrared radiation flow around the near surface. And as I think Kim also mentioned, the re-radiation, the greenhouse effect is simpler than simply decreasing the energy emitted to space. It's much more complicated, but if you try to do the same calculation for Earth, as I said, you calculate that the Earth is sub-freezing. We know that's not true. It's only when you include the presence of greenhouse gases that you can calculate the correct temperature. Similarly, for Venus, we would undercalculate the temperature by several hundred degrees because Venus has such a thick atmosphere, largely CO2. So the greenhouse effect is real. The issue is, of course, that we're adding greenhouse gases. Now, the classical graph, it's been said many times that this is perhaps the only scientific graph that's been shown in the White House from time to time over the last 20 years, is this one. It represents, each of these dots represents the average of measurements taken about every hour on the slopes of Mauna Loa, and done almost entirely by Dave Keeling over the course of his career until he died 2.5 years ago, and it's been continued by his son, Ralph Keeling, who was one of Jim's students, and by any number of other scientists around the world using all kinds of independent techniques. There's no question that you got this kind of a behavior of CO2. Now, I can remember around 1970 when I first met Don Stedman, we were trying to do some calculations having to do with acid rain, and we thought we'd start with the carbonic acid content of acid rain. So I asked Don, how much CO2 is in their atmosphere? So he went to a book written in 1963, the first book written on atmospheric chemistry by Christian Junge, who was a Max Planck Institute director, and it said 310 parts per million. So Don told me there were 310 parts per million. So Junge's book written here was talking about the late 70s. You've all heard the story how when Al Gore was an undergraduate at Harvard and Roger Revelle was teaching a course, he showed the first couple of years of data back here showing that CO2 was increasing. But the number was around 316 parts per million. And as Jim Anderson said earlier today, the globally average number in clean air is something between 385 and 390 parts per billion. And that we know about the time of the Industrial Revolution, the number was about 280 parts per million. We know that from dated ice cores taken in areas of high snow and ice accumulation so that you can get a high time resolution in the dating of the samples. So direct measurements of gases trapped in ice cores tell us how much CO2 there has been in air over the last couple of thousand years, in fact back 700,000 years. We know that in periods of glaciation, the carbon dioxide amounts were about 180 parts per million up to about 200 parts per million. In the interglacial warm periods of the last 700,000 years, the carbon dioxide amounts were between about 270 and 290 parts per million. So this is well out of the range, and Jim Anderson showed you some of those data. Now the other thing about this, well, we'll skip all the annual cycles caused by photosynthesis and respiration and decay and just look at the underlying trend. The red graph is actually data from the South Pole because the annual cycles there are so small, the seasonal cycles. The underlying trend tells you how much carbon dioxide has accumulated in the air every year, and it turns out to be approximately the same as that produced by fossil fuel burning, only it's really only about 60%. So every year, in fact, the number is surprisingly consistent. Over this 50-year period, the fraction of the CO2 released in fossil fuel burning that is visible in the air from accumulation each year is about 60%, 57, 58%. And I'll tell you where we think the rest of the carbon dioxide goes later. This is not the only greenhouse gas that humans are influencing. This is a section of data over the last 30 years of nitrous oxide at a number of stations around the world. These are now parts per billion, dry air mole fraction, showing again essentially a factor of 1,000 less than carbon dioxide. But nitrous oxide is also increasing. Similar story with ice cores. That going back to the Industrial Revolution, the ice core record of nitrous oxide was off the chart below. We're not quite as sure where the nitrous oxide is coming from, but it's certainly related to the global nitrogen cycle, fixation of nitrogen, assimilation of ammonium into plant material and animals, then death and decay, nitrification, denitrification, releasing N2O. So, and of course, nitrogen fertilizer is very, very important in producing world food supply. We're now producing more synthetic nitrogen fertilizer than natural nitrogen fixation produces by about a factor of 2. And as human demography, the protein needs are highest in the teenage years. As long as we have a young and growing population, the demands for nitrogen fertilizer are going to be great. You know, it's an expensive product, and one of the holy grails of many people is to try to produce nitrogen fertilizer microbially using tricks from molecular biology and genetics. And we hope that works someday. It will save a lot of money and energy and natural gas. But the exhaust end of the nitrogen cycle that releases the nitrous oxide back into the atmosphere will continue to work, and we expect to see probably increasing rates of release of nitrous oxide into the atmosphere. About 25 years ago, several of us were trying to figure out the role of the other trace gases along with CO2 and how they would increase in the future. And at that time, we calculated that these other trace gases like chlorofluorocarbons and nitrous oxide and a few others would essentially double the carbon dioxide greenhouse effect. And fortunately, it has turned out to be slower than that, largely due to the control of chlorofluorocarbons. Well, I'm going to start to move more into science policy. You've heard some really complicated things today, and I doubt there are many people in this room who understood every detail of every presentation. That's the way science works. We go deeper and deeper into our specialized fields, and it's wonderful and impressive, but it's increasingly difficult to communicate with the public because there's so much vocabulary, so many concepts, and so much of an empirical base that we do. It gets harder, so we have to establish a framework. Should the public care about any of this? And you've heard the energy picture. Well, one very interesting guide to scientific policy that was developed, and of course we never show them the integral signs, but the gist of it is a way to compare all of these radiatively active greenhouse gases that have the property of being infrared active between about 6 micrometers and 16 micrometers, where the bulk of the outgoing planetary radiation is. It's called a global warming potential, and it's the ratio of 2 integrals, where X represents the concentration in air of a gas in response to a pulse of an input. So if you put a puff of, say, a chlorofluorocarbon into the atmosphere, X of t describes the way it decays. So if it were a simple single time constant, and there were a rate of decay, let's say 100-year lifetime, then the response to an impulse function would be an exponential decline with a 1 over t time constant of about 100 years. So that's the impulse response. The A is the radiative efficiency of each gas, which stems from its infrared signature, line intensities, pressure broadening, band intensities, as it turns out, pressure broadening effects, location in the spectrum, and whether or not that particular absorption feature interferes with some other absorption feature that's competing for the same infrared photons. And the integral from 0 to TH is a measure of the effectiveness then of that gas due to its concentration and its time decay multiplied by the spectroscopic properties, of course measured in the laboratory, integrated over some time horizon. And this global warming potential has been adopted as a way to compare all the other greenhouse gases with carbon dioxide, taking carbon dioxide as the normalization, integrating over some time horizon. But you heard earlier today, I think it was Nate Lewis? who was it who talked about the different time constants of carbon dioxide? That you can begin to see that even this tool doesn't get you a clear answer. So I'm going to show you a few of these numbers now. And this is a little hard to read, but you see carbon dioxide across the top. And I said multiple time constants. But there's certain numbers for radiative efficiency measured in watts per square meter per part per billion. And then the so-called global warming potential integrated over 20 years, 100 years, and what's the other one? 500 years. And by definition, carbon dioxide is one. But now compare other greenhouse gases. Methane. The lifetime is fairly definitely known to within probably 15%. It's due to hydroxyl radical attack on methane. It's pretty well known to be about 12 years. And its global warming potential is 72 times that of carbon dioxide, meaning a mole of methane is 72 times more effective as a greenhouse gas than a mole of carbon dioxide injected. However, if you integrate over 100 years, the number comes down to 25. And if you integrate over 500 years, the number goes down to 8 because the methane pulse has decayed. Well, why have we settled on this 100-year time horizon? It's been just putting a finger to the wind, saying 100 years seems more relevant for human policy response. But in fact, it might be easier for us to manipulate methane concentrations and to cause a decrease in atmospheric methane in 10 years than trying to do things that are going to affect carbon dioxide over 100 years. I only want to point out a couple more of these numbers. Look at nitrous oxide. Global warming potential of between 300 and 150 times that of CO2. So even though the concentration is a factor of 1,000 less, the impact of N2O is not 1,000 times less than carbon dioxide. It's only a multiple because of this large global warming potential. Look down at the bottom, though, at the synthetic chemicals. Carbon tetrafluoride, which I don't think I ever had more fun, maybe a little bit more in research than calculating properties of carbon tetrafluoride back in the 70s. I calculated that the survival time of a carbon tetrafluoride molecule in air is tens of thousands of years. In fact, it takes some really exotic excited state chemistry in the upper reaches of the atmosphere to destroy the stuff, as you might guess. There are very few carbon-fluorine bonds known in nature in the first place. This is really synthetic, symmetric, and it has very strong infrared properties so that its global warming potential, if you integrate only to 20 years, is 8,600. If you integrate for 500 years, it's 18,000. Recently, it's been shown that sulfur hexafluoride has a global warming potential just as large, even larger, due to its spectroscopy. And a new calculation just earlier this year showed that nitrogen trifluoride, Michael Prather and his colleague revised earlier numbers to show that nitrogen trifluoride, which, by the way, has not been included in anybody's work previously as a greenhouse gas needing a policy response. Interestingly, nitrogen trifluoride is used in semiconductor industry for cleaning and as a fluorine donor for etching in a way to replace perfluoroethane and carbon tetrafluoride. So these are some inadvertent things that happen. They cannot be completely ignored, and I'll show you just one graph. These calculations are now fairly easy to do, and that is, if you'll remember those numbers from my first cartoon graph of the energy budget of the planet, it shows that the combined effect of these greenhouse gases is about 2.6 watts per square meter now. That's due to the concentration increase that's been observed in the last several decades, an increase which is due in every case to human activities. Fossil fuel emissions of carbon dioxide, I'll give you a little bit more detail that. Methane is the second most important greenhouse gas. And Kim pointed out that black carbon is estimated to be somewhere in here now, much more uncertain but significant, and so forth. Anyhow, this total extra forcing is about 1.1%, 1.2% of the solar constant. You can pick up encyclopedias and read about geological changes, and people have speculated that the sun has caused. Now, Jim gave more details on this morning, but what I wanted to say is that there is no model of stellar evolution, there is no mechanism we know of that would cause the sun's output to change by this much, and that our current first principle climate models have said if it did, we would have large climate changes. So this is a significant perturbation wherever it's leading us. That is the perturbation on the planetary energy budget due to these human-forced greenhouse gases. Now, this graph is from Judith Lean. Some of you may know her. She's a physicist who works for the Naval Research Lab. She's a very good experimental solar physicist. And it shows measurements that she and her colleague in Switzerland, Klaus Freilich, have strung together from several satellite instruments showing the output of the sun, solar irradiance, total energy, total power, measured at Earth orbit. And you'll notice, those of you with sharp eyes, that this is exactly 4 times 342. There's a factor of 4 pi and 4, or 4 pi and 4, so you end up, the geometry, if you change the units, you get exactly what I said, and this is the right measure. The point of it is, it's the first time in human history that the solar input to the Earth has been measured with enough precision to be able to say, is the sun changing? Could it be causing this observed climate warming, which none of us have shown you the evidence for yet today? And the answer is no. The peak-to-peak variability is 0.1%, and I just told you that the greenhouse effect of the human-caused greenhouse chemicals is 11 or 12 times larger. This is an oscillatory periodic function, and the human-caused enhanced greenhouse effect is sustained and growing. It's not oscillatory. So until about 7 or 8 years ago, I think we were fairly free to say, maybe the sun's minor variability is causing the observed climate change of the last half of the 20th century. You can't do it anymore. This really shows that the sun's variability is not causing the observed climate changes. A few more words on methane, and then I'll get back to the main story. About 20 years ago, we did this work. There have been some modifications to it, but the red part of the pie chart shows methane release rates on an annual basis due to activities that are under the control or at least the impact of humans. And the yellow part of the curve is natural methane sources. Well, it turns out that this picture, we constructed this from a lot of direct measurements, the known lifetime of methane, and some isotopic data on the isotopic concentration, isotopic composition of methane, deuterium, carbon-13, and carbon-14, to place constraints on all of these. And I'll say that the best known number, the one we're most sure of, is the enteric fermentation by cattle at about 80 million tons of methane a year. That one is really well known and has been well known for a long time. Some of the numbers that are not so well known are rice paddies. Despite a lot of efforts, this number is still very uncertain. But the overall picture is about right, because we know that atmospheric methane concentrations have risen by about a factor of 2.5 or 3 in the last 100 years, and that's the red part. If we only had the yellow part, atmospheric methane concentrations would be down by about 70%. So the big picture fits. We think we're pretty good on the methane picture, but not perfect. Okay, now, several people mentioned related facts, but the growth rate in the use of fossil fuels to convert energy over the last couple of 100 years has been staggering, and the current number of the global release of carbon dioxide just from the burning of fossil fuel is about 8 billion tons a year of carbon. Just several years ago, it was 6 or 7 billion tons, so it's growing rapidly, and the color breakdown is just the different forms of fossil energy. Now, in addition to this release rate of carbon dioxide, there's probably another 2 billion tons a year of carbon dioxide being released by human activity from deforestation, mostly tropical deforestation for agriculture. It's not just the burning of the above-ground biomass, but it's the exposure of soil organic matter, which wasn't exposed before, which now gets oxidized and releases CO2. That release rate is more variable, but the current estimate is about 2 billion tons of carbon a year. So the total release rate is about 10 billion tons of carbon a year. And as I said, about 60% of it shows up in the atmosphere, and the remaining part of it is taken up by oceans, and I'll tell you more, and other biosphere. Now let's go a little bit closer to policy in the world. This is obviously a historical set of data with projections past 2008 into the future. And it's from a couple of other people have used this particular database. It's the United States Department of Energy Information Agency, which is a semi-independent part of the government. And they're very reliable. They've done good work over the years. We know what a few of the errors in their database are, but they're pretty good. I apologize for the units, but Jim and I have talked about this. I maintain talking to the general public. BTUs are easier. He says zeta joules are. But these are not scientific units. That's why I have to apologize. These are British thermal units. But that's what the U.S. Department of Energy uses. So in 1970, the worldwide usage of energy in all forms was 207 quadrillion BTUs. And that figure doubled by about 2002, about 32 years later, to be about 415. The current usage is 463. And you'll see the color parts of the bar, which begin to get into an interesting story. The blue part of the curve used to be dominant. And as we've gotten up to the present time, the red part of the curve, which represents carbon dioxide emission from emerging markets and developing countries, has become larger. And as we look into the future, and I think Jim may have used some similar figures today, the world energy consumption in the next 22 years, and 86% of this is due to fossil fuel, is projected to go up about another 2/3, with most of the growth occurring in developing and emerging markets, whereas the mature market economies like the United States and Canada, Western Europe, and Japan are projected to have a growth rate of maybe only 1% per year, taking into account continuing improvements in energy efficiency. Well, you begin to see where we are. The carbon dioxide that was emitted into the atmosphere in this period of time is still there, and it's almost all attributable to advanced countries, rich countries. As we move further into the future, their emission rates surpass those of advanced countries, but they can say, well, look, our per capita emissions are still much less than yours, and by the way, you've loaded up the atmosphere with this stuff that's going to survive for hundreds of years. So you can see why the international discussions on how to deal with this situation have been resulting in finger pointing. And somehow we're going to have to get beyond that. A couple people mentioned today the rate at which coal-fired power plants are being added, for example, in China. So these data are from the year 2006 from the U.S. EIA, once again, as reliable as we're going to get. There are a couple of international sources which are similar. And it showed that in the year 2003, we were pretty sure that the U.S. coal-fired power plant capacity was producing, or could produce, about 310 gigawatts of electricity instantaneously, and the China production was about 240, and so forth. The year 2010, it was projected that China would have increased by almost 50%, and the U.S. by about 3%. And then continuing to the year 2030, the Chinese number would be roughly triple what it was in 2003, and the U.S. would have gone up about 50%. But when I was putting these numbers together, I realized that something was wrong, because the growth rate in China in the last few years didn't seem to be caught. So indeed, these numbers have now been changed by the U.S. DOE's EIA just in the last month or so. These are now the updated figures for China for the year 2008. And we know that they're still not satisfying all their demand for electricity, because there are credible reports of factories having to close for lack of electricity, and not enough coal miners and everything else. So a lot of today has been spent acquainting us all with the dimensions of the problem. And when I close about what we can do, I think that's still an important part of what we're doing. Well, this is another cartoon, but it embodies what's needed to manage, if we're really concerned about the carbon dioxide carbon constraint. This portrays fairly graphically what's going on instead of writing differential equations. We have a bathtub representing the carbon dioxide loading of the atmosphere with an input being and here it says 7.2 billion tons per year, and I've already showed you that today's fossil fuel burning is already up to 8, and if you include deforestation, it's 10. So call it 8 to 10. Whereas the drain has been measured pretty well to be a capacity of about 3 billion tons a year. It's been measured by field experiments, by isotopic tracers showing carbon dioxide uptake in the ocean, by soil carbon balances, by increase in vegetation in mid-latitudes. So tropical deforestation releases CO2. The CO2 is fertilizing the biosphere in the northern mid-latitudes where carbon is being accumulated. My hands a little bit because it's not that clear, but soil carbon balances and isotopic data keep coming up with these numbers, that the natural uptake capability of the oceans and the biota are about 3 billion tons a year. So we have a system that's out of balance by 4 or 5 billion tons a year. So that you might hear someone say, well, we want to stabilize the amount of carbon dioxide in the atmosphere. All we have to do is hold emissions constant. No. Emissions have to be trimmed by 60 or 70% to hold the carbon dioxide amount in the atmosphere constant. So this is another fact that we're dealing with. Now, what is a dangerous level? There are international agreements signed by President Bush 41 that committed all the nations of the world to take actions necessary to prevent the accumulation of dangerous levels of greenhouse gases, but they didn't define dangerous. Now, Jim gave us one operational definition of dangerous today by talking about an irreversibility of change like sea level. Another kind of irreversibility might be represented by loss of biodiversity. Things that are truly irreversible, I think, qualify as dangerous. But the fact is, neither we nor the general public have done a good job of defining dangerous. And in this bathtub cartoon, the Japanese defined it as a level of carbon dioxide in the 400s because they were also taking into account the radiative forcing due to other greenhouse gases, which would mean that the equivalent carbon dioxide was probably around 700 parts per million. Okay, you've heard a lot of numbers today about the challenge of scale. If we truly wanted to reduce our emissions of carbon dioxide in terms of carbon into the atmosphere by of order 5 billion tons a year or 10 billion tons a year, because you heard Nate Lewis's rendition of the energy growth rates growing to an equivalent of a dozen or 14 terawatts. Some of you may have seen these so-called carbon wedges that Steve Pacala and Rob Sokolow prepared a couple of years ago. I'm going to now describe what a 1 gigaton carbon wedge looks like. So the target that they adopted would be reducing emissions about 7 billion tons a year, and avoiding just 1 billion tons a year would require that the energy use in every building on Earth would have to be cut 20 to 25%. Now, each of us is familiar with some energy savings in buildings on our campuses or our companies. We would have to do that 20 or 25% saving in every building on Earth to save the emission of 1 billion tons of carbon a year. Or we could increase the fuel economy of a fleet of 2 billion cars from 30 miles a gallon to 60 miles a gallon. That also will save 1 billion tons of carbon a year. And there are many other examples. If indeed we had some way to capture and store the carbon emitted from just 800 gigawatt coal-burning power plants, that would save 1 billion tons of carbon a year. And these wedges go on. They're really quite good at illustrating, and I won't go through them here. This is another example of the challenge of scale that we're facing. You can look at it in terms of energy sources to be replaced, energy efficiency to be gained, or whatever. Now, so far I've been talking as if climate is the only constraint. It is not. And if one of you were the President of the United States or a Prime Minister of a leading country or the King, you would have to look at some other constraints. For example, national and international security. There are different ways to define security, but one of them is access to energy that you control somehow in your national borders. Jingoistic phrase of energy independence, maybe. But clearly, in a practical sense, the United States coal reserves, the Chinese coal supply, the India coal supply, the supplies in South Africa are attractive for each of those countries to use, and I think it's very, very unlikely, unless, Dan, you're awfully successful quickly, that people are going to quit using coal. They're going, but whatever it is, and what would appeal to a domestic source of renewable energy, as both of you talked about this afternoon, is that it's domestic. It's one measure of national security to have control over a domestic source. Then, of course, there are international security implications of what happens to the money that people spend on imported oil and what the money gets used for. So security is a broad word, and if you were in charge, if you individually were in charge of this, you would have to take this constraint into account. It's not just climate. There are financial costs, and we all know the personal financial costs of energy, the institutional costs of hospitals and universities, cities and nations, and of course of developing countries. The development of poor countries is going to be retarded by high energy costs. So if your agenda happens to be trying to help the poor people of the world develop, this constraint is also important. There's environmental constraints, and by this I do not mean climate. I mean the kind of traditional environmental issues of scraping off mountainsides to mine coal, or spending zillions of gallons of water to fracture shale to get oil, or mercury emissions, or nitrogen oxide emissions, or sulfur dioxide emissions from fossil fuel burning. So there are many other environmental constraints, including black carbon. There is, of course, the climate constraint that we've talked about a lot today. And then if you happen to favor nuclear sources, there are the continuing concerns about the safety of operation, which many people think is not that difficult, but certainly the issues of waste, everything from the sociological and political through to the physical and containment, and now, of course, the heightened concerns about proliferation, especially if we go to not a one-pass cycle for uranium, recognizing what Nate said, that the uranium supply can become limiting if we only use a once-through pass on uranium instead of recycling. If we recycle, then we have higher danger wastes, although less of them. Okay, so with all of these multiple goals in place, if we take all of these constraints seriously, and not just the climate constraint, let's just put a couple of sample goals up. If your goal is to assure energy supply, then the preferred pathway might be the use of domestic coal, or wind and solar, which, as Jim Anderson pointed out today, the U.S. is particularly fortunate. Non-agricultural biofuels, as in Brazil's case, where sugarcane is an agricultural crop, but they've been able to extract biofuels from it successfully without displacing necessary agriculture. Nuclear power, drilling question mark, because it's very, very unlikely to assure an energy supply. And efficiency with an exclamation mark. If instead your goal for energy policy is to reduce carbon dioxide emissions, both to mitigate climate change and to slow down the acidification of the world's oceans, then you end up with somewhat different energy choices. Renewable sources look like a winner if you can satisfy the challenge of scale and do it quickly enough. Nuclear power looks like a winner. It brings carbon capture and sequestration onto the table. If it weren't for the carbon constraint, I don't think anybody would be talking about carbon capture and sequestration. In fact, people who think that this is going to be very difficult still have to admit that it is a worthy and necessary goal if you take this constraint seriously about carbon dioxide. And then efficiency is a winner again. Well, there are two other strategic challenges which we've glossed over a little bit today, although everybody understands them. that having renewable sources of electricity, for example, don't help us with today's transportation fleet that is based on the internal combustion engine with liquid hydrocarbons. And there is an advantage to liquid hydrocarbons, namely that you don't have to carry the oxidizer with you, so that you get about half of the mass that's necessary for the combustion for free out of the air. So the point is, when you look at today's situation, and for the perhaps next 10 years or so, until and unless there can be an electric drive fleet, reducing oil used for transportation is a strategic challenge. And similarly, reducing the carbon dioxide emissions from coal-fired power plants is a strategic challenge, given the likelihood that we're going to continue to use coal. So these kinds of observations, which are easy for us, as you learn anything about energy, are more difficult for politicians. And it's not because they're dumb. It's because they're not specialized. They're dealing with 100 issues at once, and they want to believe that there's a simple, easy, maybe not easy, but simple solution. Do one thing and do it well, and we'll solve all the problem. And they have to be reminded. For example, one of the presidential candidates is talking about solving our energy problem by building 45 nuclear power plants. Well, you might get enough electricity that way, but with our current transportation fleet, it's not going to help the internal combustion-driven cars that we have on the road for the next 10 or 15 years. So there are transition steps here also. Energy efficiency, though, for the life of me, I don't see why we haven't been able to do more with energy efficiency. And here I distinguish not conservation. Conservation is when each of us saves energy out of our own goodwill and eagerness to save money. Efficiency is more a technology matter. But it's a win-win situation, because increased energy efficiency would satisfy so many of these goals. It would decrease our dependence on foreign supplies, and this is true for any nation, not just the United States. Improve not only national security, but international security. It would decrease our trade deficit, which at about $75 a barrel, I think our trade deficit just on oil alone is about $350 billion a year. It would decrease local air pollution. It would increase national competitiveness. It would encourage the development of new products, just high-efficiency products. It would decrease household energy costs, and it would also slow down the increases of carbon dioxide and methane. So why aren't we doing more with energy efficiency? The answer seems to be that there are barriers between people who need it and people who can supply it. For example, business owners who can see the bottom lines that people like the McKinsey consultants have given them on how much money they can save on energy, but they don't have the technical staff. They don't know what the capital costs would be. So we need more energy service providers to fill these niches, to bring existing technologies into place, to make the kinds of connections that, Dan, you were alluding to with the visits you've had from companies who have technologies that won't work without some other piece in place. However, I want to give you a couple of examples of just how much science and technology can do, even without a lot of political and business cooperation. These are some measures of the traditional air pollutants that Kim mentioned this morning, that particulate matter, especially its chemical composition, has not been used as a measure of air pollutants because nobody's been able to measure it well enough. We have data like this going back 30 years on ozone levels. This happens to be Southern California, carbon monoxide, some particulate matter. And then in the red curves are vehicle mile traveled. This is a 20-year difference now in Southern California, showing that vehicle miles traveled per day or per year went up almost 60% in this 20-year period. The population went up nearly 40%, and yet these measures of air pollution were decreased. 40-some% for ozone, 50% for carbon monoxide, even though they didn't adopt Don Stedman's beautiful ideas. The measures of ozone, much more specific kinds of measures of ozone pollution, the data go back 30 or 40 years, that most measures of air pollution have increased, even though human behavior has gotten worse, with, say, 400% increases in vehicle mile traveled. How did this happen? It happened due to better formulation of fuels, cleaner fuels, better automobile engines, better machining, and emission control devices, all of which was science and technology. People didn't change their behavior. In fact, they're driving more vehicle miles in higher powered vehicles as well, but with less air pollution. And this came from science, this improvement came from science and technology. It didn't come from human behavior. So while we definitely need improved cooperation, better governance, better incentives for business, better tax policies, better ideas at the local level on how to incentivize homes to be built with insulation in them rather than having the builder in the position of building a house without insulation because it's cheaper than passing on a poorly insulated house to a customer who wants a house at a lower price. We have to intervene at local levels too. All of that is needed. But in the meantime, I think our biggest gains are going to continue to be from science and technology. So what is it that we should be doing? Well, today's a good example of educating ourselves and doing what half of the people here do, and that's educate students. Because many of the issues we're facing are going to be long-term, and it's going to take an enormous public resolve, and it's going to have to be led by the educated public, whether they be business leaders, whether they be non-government organizations, private individuals. Education is a huge part. But strictly from a scientific point of view, we have to identify and analyze options. Now, scientists have been pretty good at identifying and quantifying problems. I'm skipping over that, like the whole carbon cycle, one in climate change. But scientists have to identify and analyze options. The kind of thing that Nate did earlier today, showing the different energy pathways and what you can possibly get out of optimum application of various technologies. We have to create realistic options. We have to compare them quantitatively, and we have to do a much better job of communicating with leaders and the general public. This is not just feel good. Every one of these actions is going to have to happen. Certainly, the kind of energy research that has been discussed today, from renewable fuels and then carbon capture and sequestration, a lot of fundamental biology can still bring about, and things that are in sight, from genetic modification of crops and other non-food crops to get liquid biofuels much more efficiently. A lot of nuclear issues, energy storage, I guess that was Dan's one word, and then many more challenges. So we have a huge agenda. I'm not going to talk in detail about what's going on now, but I would say in Congress there is more awareness than I've ever seen in my lifetime over the energy challenges driven by all of these goals: energy security, costs, and the climate change. There is also a lot more awareness than I've ever seen before of the fact that there's no silver bullet. It would be delightful if one particular technology and renewable energy can satisfy all the needs. But even if it can in the long run, we still have the minor problems of converting our transportation fleets off of internal combustion engine. So the good news is there's more awareness than ever before. I think people have felt the threats, and there are enormous business incentives, absolutely enormous. I think the real reason that person was sitting in your office that morning, Dan, is not that she thought that you were a star and she wanted your autograph. She saw some opportunities, right?
I gave her my autograph.
Okay, good. Well, you're especially kind. How can we bring this all together? I don't know, but I do really believe that scientists and engineers are going to have to guide the formation of all of these options, to quantify them, to figure out the inadvertent side effects, including things like geoengineering, and at every stage guide policy development of businesses and government. And I think we're going to have to do it every month and every year. It's not going to be something that happens in Congress every 2 or 4 years. It's going to be continuous. It's just an enormous challenge. I myself was staggered with some of the numbers I heard today, because as familiar as I am with the scale, I heard different ways of depicting the numbers which were just mind-blowing. So let me stop here and thank you again.
We We have time for a couple questions if anybody has any. Jim?
You can't not ask questions.
Yes, you can.
Yeah, Ralph, I think one point that we should make here to keep things optimistic at the end of the day is to recognize the fact that this issue is no longer a Republican-Democrat issue. This is an issue of coherent national security, fiscal policy, foreign policy, energy policy. And there's a tremendous amount of motivation now to solve these, which are all solved in largely the same way. You picked out conservation as one of them, but this really applies across all aspects. And I think it's an issue now that there's a great deal of hope for, because it isn't this issue that divides the House. And I think this is going to be a very important point. The other issue that I would like you to comment on is the non-existence of a federal program to both study energy and to study the climate. I mean, it's a little bit like one of these Western storefronts. You know, it looks beautiful from the front. You look around the back, and there are dead chickens and dust blowing around, and it's a non-existent, pathetic treatment of a very serious problem in both energy and climate.
Well, I agree. There's probably less partisanship now than there was a couple of years ago. But there's still some questions which are going to tend to divide on political grounds. For example, the introduction of new energy technologies. We're still in a position where a lot of the oil in the world is controlled by companies whose extraction cost is a small fraction of what they can sell it for. So they can lower the price on oil at will. In fact, some of us were talking about Vinod Khosla. Some of you know him from California. He's one of the very, very bright venture capitalists. He was a partner in Kleiner Perkins, who's working on liquid biofuels and supporting research in genetics and molecular biology. And he was personally told by leaders in Saudi Arabia that they could wipe out his investments anytime they wanted by lowering the price of oil. Now, why do I say that? Because I think that's a fact, and that a lot of other people are going to have to be convinced that the market alone will not solve these problems. It's going to require some government action, and we've seen any number of corporate leaders asking for the federal government to set rules. For example, a price on carbon. There are many technologies right now, all of them are uncompetitive with carbon as a source of electricity. Coal. So unless some kind of a floor is placed on the price of oil imports, or some kind of an extra price is put on carbon, most technologies are not going to be competitive with coal as a source of energy. And that begins to get you into an ideological issue that some people say that that's not an appropriate role for government. So I agree with you, it's getting better, but there's still going to be battles.
Thank you for the comment, Ralph. I just wanted to point it out that when you put liquid fuels in your car, you put about a full tank is about 50 pounds of gasoline. That gives you a license to burn 750 pounds of air, which you didn't have to pay for and you didn't have to carry along. Liquid fuels are amazingly advantageous for transportation purposes.
That's true.
Just a very quick question. Since it is the political season, and you mentioned that hopefully we're going to be bipartisan about solving the problem, I think it was in the first debate when the two candidates were asked, do you think we're going to solve some of these problems because the government is going to invest something? Let's use the Sputnik era challenge that we had a few years ago, or is it going to be a garage door industry where entrepreneurial effects are going to have to take over? We'll put you on the spot about candidates, but just your perception on how we're going to get it done.
I honestly think that both approaches are needed, because although the prevailing view right now is that we have a series of challenges across the board that are really quite practical, there's still that possibility that someone's going to come up with a great new idea, and I think we have to invest in all of it, because as everyone showed the numbers today, we're not going to get home free here unless we exploit basically every possibility we have, unless there is some fantastic breakthrough in renewable electricity and storage. And you know what Dan talked about, a complete revolution where everybody converts their own energy or generates their own electricity. And we go away completely from the electricity distribution grid. It also means that the grid itself has to change, and that brings in thousands of practical problems. So I think an across-the-board full court press of increasing efficiency, of developing every technology, of placing a price on carbon, and of doing basic research. We're not going to get there because there are all these constraints. There's going to be a tremendous push to use our domestic coal, whether we like it or not.
We get one last question.
Okay, just very short. I like to also just point to, I like to blame ourselves. And for the simple reason, and I agree, we're going to need government intervention, but there are too many people in science saying, just take what we have and then use it, put some intervention in so it will get adopted. And what I will say is we spend a lot of time giving the numbers, but we aren't doing our job well enough. You get something cheap, I guarantee you will not have to worry about any government intervention. There is so much money to be made. And so I just, in everything in my life, my finger always ends up pointing at myself. And I don't think our community has done a good enough job to make it cheap so people will use it. So we better get to work now.
Get to work.
Okay.